Okay, so let's get started. Tomoyuki Yamakami will be kicking off our CSP
Okay,
session.
well, good morning, everyone. So I'm going to talk about the approximation classification of the complex weighted counting CSPs. And before going into the business stuff, I'm just to give a bit of information about the University of Fukui, where I'm currently teaching. Fukui Prefecture is around here. The Japan is composed of 47 prefectures. It's more like the state in the United States. So the Fukui Prefecture is here, the Tokyo is here, and Nagoya is here, and Osaka is here. So that the Fukui Prefecture is closer to Osaka than Tokyo. And, by the way, it takes about 3.5 hours from the Fukui to Tokyo, because there is a big mountain here, so we have to make a big detour to get into Tokyo. So that's the kind of bottleneck sample. And this is actually the picture of the Fukui Prefecture. Someone said that this is a tadpole, like a head here, sort of thing. And the Fukui city, inside this Fukui Prefecture, is located around here. And I just enlarged this area. So this is actually the central part of the Fukui city. And there are 3 train companies running those business here. And the biggest one is actually this line here. And this is the Fukui railway station. And the university has 2 campuses, one here and another one is here. And the computer science department, or we call it the Department of Information Science, that is actually located in this campus. So this is just a bit of information. Now we have to go back to business. So my target is the counting constraint satisfaction problem, sharp CSPs, on the Boolean domain. So that we want to use 0 and 1 as a domain. And our goal, the first goal is to give a complete classification theory on the computational complexity of approximately solving complex weighted CSPs. Yesterday, there are several talks about the exact counting case. But here, I'm focusing on approximation complexity instead. And the second goal is to give us an alternative proof to the classification theorem. The important thing is that actually this proof does not consist of an auxiliary free unary constraint in the most part of the proof. Okay, so the following talk is based on 3 papers of mine, those stuff. The last one is actually presented a month ago in the conference. And actually, you notice the whole thing about the constraint satisfaction problem, and also there was a tutorial yesterday. So I just quickly go over just to remind you what this means. Constraint satisfaction problem. Well, this is just a simple example here. So that an F is a logical formula in a CNF form, and this is actually an OR of, it's an AND of 3 ORs. So this is written by like a functional form. It's a multiplication of 3 ORs. And major question about this F is that we are wondering whether we have satisfying assignment for this F. And if there is a satisfying assignment, then, we can ask how many of them. And sometimes computing an exact number is very difficult. So that we actually relax our condition so that we can actually approximate that number in some efficient way. Now, another way to express the same problem is that we use the bipartite graph with labels. The labels are actually left side of this bipartite graph, and we have variables. And the right side, we have constraints. And the connection of this constraint, for example, the first OR has x1, x4, x3. So we have a connection to the variables in the left side of this graph. So now, Boolean variables, and we have an unweighted constraint. And the previous question is rephrased as following. in the following way. So the first question is about the existence of Boolean assignment that satisfy, that make those this multiplication to be non-zero, or actually 1. The next question is the number of the satisfying assignment. That is the actual calculation of the sum of this multiplication. Because if the tuple, the 4 tuples satisfy this one, and that's going to be 1. So the summation of the sum of all this multiplication is exactly telling you how many satisfying assignments. The decision CSP asks is formulated in the following way. So the instance to this question is before that, we had to specify the constraint language. The constraint language is the set of constraints that we can possibly use. So instance to the decision problem, CSP of F, is a pair of variables and constraints. And the question is, as I said, we are asking whether there exists truth assignment, satisfying assignment that make this all F to be true. So the typical example of CSP of F is satisfiability problem and vertex counting problem and so on. Now the counting version of CSP has the similar structure here. Instance Boolean variables and constraints taken from capital F. So F is the set of constraints. And now question is how many variable assignments satisfies all the given constraints. So this is our question. So typical example that belongs to sharp CSP is sharp SAT. This is the counting version of satisfiability problem, and counting a bipartite independent set problem. So this is actually bipartite, the independent set problem restricted to the bipartite graphs, and the counting downset problem. To describe the instance, input instance to this problem, I just kind of came up with the new terminology. It's a constraint frame. Constraint frame actually saying that we have this picture, the graph, the bipartite graph, and all the labels. And our target is to compute this value, so the CSP sub omega, summation of the multiplication of all the labels. So now our instance is a constraint frame given like this one here, and our task is to compute CSP sub omega. And previously it's in an exact counting case. So we actually exactly counting this value. So in that case, we have a number of the results. The earliest one is 1996, the dichotomy theorem about the unweighted Boolean CSPs. Professor Herman actually told me a very nice story about what happened when you submit this paper to the conference and journal. That's a kind of interesting story. If you're interested, maybe you can ask him. Then in year 2009, another dichotomy theory. That's actually an extension of this early paper, and they talk about the non-negative weighted Boolean sharp CSPs. Right? Okay. Then this is actually expanded into the complex weighted Boolean sharp CSPs, and all of them they have dichotomy theorem. And so the dichotomy theorem means that we only have either two levels. In the bottom level, we have polynomial time computable counting problems, and then the other one is just consisting of sharply complete counting problems. In a standard complexity theory classes, we have possibly infinitely many levels between tractable problems and intractable problems, assuming that an FP is different from sharp P. But the constraint satisfaction problem, we have only 2 levels. This is actually very nice and surprises a lot of people actually whenever I talk about this one. Now we are moving on to the approximation counting. And before that, I have to actually explain about it and how to handle complex numbers, because then our target is complex numbers. And slightly different from the computational complexity theory, the standard way of dealing with complex numbers in computational complexity theory. I just treat complex number as an object. So I don't care about it and how to represent it. So the complex numbers are being treated as objects. So we apply the multiplication, addition, division, those operations, natural operations, taking only unit cost. So basically, we are counting the number of possible operations to get the desired complex numbers.
Can you do equality?
Pardon me?
Can you do equality? Like equal? Can you check whether 2 complex numbers are equal?
Yeah, that's right. Yes, in just a unit time.
So you define some logic over complex numbers?
Mm-hmm. So, yes. Well, so why this, so I just take this framework because, there are several ways to represent complex numbers. And then, if I just build a theory based on one particular representation, then, I have to translate that representation into another if I just, developed another theory on it. So, but then if I just treat it, all the complex number as just an object, then I can simply use any possible representation.
Can you distinguish the reals inside the complex number?
Yes, you can distinguish between the real numbers and complex numbers in unit time. So no, that's just assumption. Then, based on this representation, this is one of the representations. FP sub c is the set of all complex numbers computable in the polynomial time, and sharp p sub c is the counting version of it. So now,
Sorry, what is sharp again?
sharp p is the set of all complex functions computable by counting machines in the polynomial time. The counting machine is the basically it's a non-deterministic Turing machine. Actually, either ending up either accepting or rejecting.
But is it the same as Klaus-Weier's definition? Let's talk about this.
Which one are you talking about? Sorry, I just missed your word.
Over the complex numbers.
Yes, complex numbers. Yeah,
Same as the one used in
Are you going to give a more detailed definition later of what?
Oh, no. This is just a definition. Yeah. Yeah, that's right. I'm not really. I just introduced those notations, but those are actually, simply, describing, the problems, and I'm not really kind of taking out any particular property that belongs to the sharp p sub c. So this is actually, a complex extension of the standard sharp p. Standard sharp p only deal with the natural numbers as an output, and I just simply extend it to complex numbers.
So what is a complex function? It takes a bit string to a complex number?
The inputs are, here we actually didn't deal with the inputs are complex numbers and the outputs are complex numbers. And the randomized approximation schemes to deal with approximation of the some particular function or problems, so we have to use an approximation scheme. Here is the approximation scheme I'm going to use. Suppose that f is a function from the sigma start, and sigma is the the finite set of the object, and C is the complex numbers, the set of complex numbers. And F, this is considered to be the counting problem. Counting problem actually is an output the complex numbers from the input instance. So this function F is a randomized approximation scheme. F has the randomized approximation scheme if there is a probabilistic algorithm that actually satisfies this condition. The input to this algorithm is in a pair. X is the standard input, and epsilon is the error parameter. And output of this algorithm is in the W, and that satisfies the following condition. The target is in f of x, and we are actually approximating this value using this W. So that in the W, the relative error between the W and the f of x is bounded by 2 to the epsilon. More specifically, that we satisfy this condition because we are dealing with complex numbers. So this is actually the real part, and this is about the complex imaginary part. This is the argument of the two complex numbers. This is just a simple extension of the standard real number approximation scheme. And to compare the complexity of the two counting problems, we have to introduce an AP reduction. So AP stands for an approximation preserving reduction. That is introduced by Dyers, Goldberg, and Greenhill and Gerard in 2003. And we actually slightly modifying this reduction using the complex numbers and apply that into our situation. So basically, we transformed F into, we calculate F, counting problem F, using counting problem G, using the Turing, Oracle Turing machine. And the input to this machine is the pair of X and epsilon, as before. And assuming that there is the Oracle that computes G using randomized approximation scheme, then we can actually compute f of x in polynomial time. Then we will use the notation like this one here. The f is AP reducible to g using this less than or equal notation. And for example, the counting down set is equivalent to counting bipartite of independent set. And this is reducible to sharp SAT. Now, then approximating sharp CSPs. We have several results. An early result is in 2007, they proved the trichotomy theorem for the unweighted Boolean sharp CSPs. And after that, I thought about how to extend this result to complex numbers. And then I came up with the solution of the dichotomy theorem instead of the trichotomy theorem for the complex weighted Boolean sharp CSPs. But I'm assuming that I can freely use an auxiliary free unary constraint, use E. So this is actually the precise statement of my result. The f is any set of complex valued constraint. So we fix this. If f is contained in ED, then ED is a constraint set made up of, later on, I'll just give a more precise definition, but basically ED consists of the binary equality and the disequality and any unary constraint. And then this problem is solvable in the polynomial type, the polynomial type computable problem. And if not, then all the problems are actually reduced from sharp SAT, so that these as complex as sharp SAT, C. C stands for the complex version, complex number version of sharp SAT. So if I just simply compare the two results, in the early result for an unweighted constraint counting problem, there are three levels, basically. And here, so we only have 2. So all the problems here are actually turning into a very complex in this situation. Now, I'm kind of running out of time. So I'll just quickly sort of go over the very basic stuff. The constraints, so I'm going to use this notation to represent the constraint. For example, the OR is 0, 1, 1, 1. It implies it's 1, 1, 0, 1. Implies stands for the logical implication. And XOR, equality, and NAND, so on. And for unweighted constraints, like equality and implies, we have a very nice result here. And those are very, some of them are very simple, some of them are very hard, and some of them are actually in between. And we are very interested in the use of the unary constraint. Unary constraint is a function with one variable. So if you just draw the constraint frame picture, those red nodes represent unary functions. And particularly in all unary constraints, we actually recognize 2 particular unary constraints. Those are actually called the constant unary constraint, delta 0 and delta 1. Delta 0 outputs 1 when x is equal to 0, otherwise outputs 0. Delta 1 is on complement of delta 0. And constraint being symmetric means that when we permute the order of the variables, but still the output of this constraint f is the same. For example, the 0, 0, 1. Suppose we have a 0, 0, 1, those assignments, and another assignment 0, 1, 0. F outputs exactly the same value. To describe symmetric constraints, we use bracket notation instead of the parenthesis notation. And so x1, x2, x3 represent the case, the x1 is the outcome of f of 0, 0, and the x2 case, well, we have the assumption that the constraint is symmetric, so that the 1, 0 and the 0, 1 case, both have exactly the same value, and so on. So we simply put those numbers. So this is actually the succinct notation to represent the symmetric constraint. For example, the OR is actually now written to 0, 1, 1 instead of 0, 1, 1, 1 in the parenthesis notation. And we are going to use the unary constraint as free object, so that whenever we actually get the input. Input is the variable and the constraint, right? We can freely add extra unary constraints. Unary constraints are actually used in many different authors and papers. And in later slides, and I'm going to use a succinct notation. If you, U stands for the set of all the unary constraints. So that adding U to the input, the constraint language F, it means that we actually can freely adding extra unary constraint as a part of input. So we use an asterisk notation instead of the writing U, whenever it is possible. Now, I'm going to describe the result here. ED consists of an all constraint whose that is defined by defined as the multiplication of the equality, disequality, and unary constraints. And IMP stands for the set of the Boolean valued constraint. Those are actually multiplication of positive number of the delta 0, delta 1, those are constant constraints. and implies. IMP stands for, comes from the word implies. And now the constraint we are interested in are actually the complex valued functions. So now we assign Boolean valued relation or constraint that corresponding to f in the following way. If the outcome of f is equal to 0, then we simply make this r sub f to be 0. Otherwise, output 1. So that we are actually judging whether f outputs 0 or not. And this underlying relation belongs to imp. Then we call f as imp support. The imp stands for the implication. So now I just list the first dichotomy theorem here. Now we have U here. Now the proof of this theorem is actually broken down in the following way. So suppose an f is contained in an ED, then we directly compute the counting problem, sharp CSP of f comma u in polynomial time. So that's actually fall into the tractable case. Now, otherwise, we simply choose f that does not belong to ED from f, and then we split into the two cases. Suppose an f has an imp support, then we directly go into this one here. And if does not, in the case that f has no imp support, we have to split into two cases. And if f has non-zero entry in the bracket notation, then we actually come down to this conclusion here. And also, if f does not have a non-zero entry, then we use a little bit of detour, but then we actually get this one here. And then once we get this one, we use this well-known result to get the final result. I think that I'll just skip the main part of the proof here. And the core is, we actually use an induction. And the base case is very simple. And the second, when the case k is equal to 2, then we will use the AP reduction. And the induction case, so this is actually the core of the proof, and it takes somewhat 10 pages or so. And I just skip a couple of things. And here. And now I want to explain about the second theorem. And that actually gives an alternative proof to the first theorem. To do so, first I have to clarify that our ultimate goal is to give the complete classification of the counting problem without any additional free constraint. To do so, I have to analyze the first theorem. But the first theorem, as you remember that that is actually case by case study. And if there's an f has an imp support, and if f does not, and so on. But there is no clear the discussion that where we need u, it's a unary constraint, and where we do not. So first, I had to really think about that proof, and to clarify those the importance of the unary constraint, and we have to actually build up with the different proof. So that is an alternative proof. Now, to explain that, I have to introduce several more set of constraints. The first one is the degenerate constraint. That the degenerate constraint means that just a multiplication of the unary constraint. So basically unary constraint. And DG minus means we actually simply put a limitation, restriction on this set. So we only allow this form here. And ED1 is similar to the ED, but we use these constraint. And the ED1 plus means we actually simply expand this definition. For example, in the first definition, we will take the x comma x or x comma minus x. Then instead of using this plus minus x, we use any y instead. So then, this is a little bit extension of this ED1. So that's why the plus signs is actually added here. And AZ stands for the alternative zero. So that we have alternative zero, alternating zeros, starting with 0 or x. And or is the, well, basically it's an or, extension of the or. But here, x, y could be any numbers. Oh, sorry. Well, before that, I have to limit, restricting my attention to real numbers. Because a complex number, discussion of the complex number is a little bit more complex. So that I just simply put the limitation, restriction on the use of complex numbers. And B is the set of constraints of the following form, x, y, z. And x, y, z are non-zero, and x, z is not equal to y squared. So now the second theorem says, suppose f is a set of an algebraic real-valued symmetric constraint, so that we have tons of restriction here. But the statement is something like this one here. If f is either contained in this union or this union, then sharp CSP of f without u is solvable in the polynomial time. So there is no use of unary constraint. And otherwise, there is a constraint, a particular constraint of this form. Do you remember that B has this form and or has this form? And such that this counting problem is AP reduced from sharp CSP of G. And what is the connection between this theorem and the previous theorem? So if you add U to those problems here, so that in the first case, DG union ED1 plus, and if you add U, but still U is a part of the DG, so this problem belongs to FP. But second part, even though this class actually to make the sharp CSP solvable in the polynomial time, but an addition of U make it very hard. Just one or two more slides. And the last one is that actually adding U make this problem very difficult. So that this actually goes back to the first theorem. And the proof goes like this one here. This part is the actually direct calculation. So we just simply give an algorithm how to calculate, how to solve this problem in a polynomial time. The core is this one. If f does not satisfy those things, then we actually build a particular g that satisfies this AP reduction. And after that, so this argument does not depend on the use of the unary constraint. The unary constraint appeared here to get the first classification theorem. So the problem here, well, this is actually one result. But to get into the ultimate goal, to get rid of those U, this part has to be broken down into more precise characterization or classification. Because we know that some G belonging to this one actually make the counting problem easy in approximation sense. But the other is actually really hard. So that this does not completely resolve the ultimate goal. So that's actually the problem. But this is just the first step, getting into that direction. And to prove that theorem here, we actually use this approximation lemma. This lemma says from F is a non-empty set of algebraic real-valued symmetric constraint. From this F, we can approximate delta I. Well, delta I stands for either delta 0 or delta 1. But we don't know which. But at least we know that at least one of them is approximable from this set. So we use this lemma many times to get into. Oops. Oh yeah, this part. So this is actually given by the elimination of the delta 0 and delta 1. That's it. Thank you.
Okay, maybe time for one question while David's setting up the next. Where is David? Oh, it's there. Any questions? Remarks?